Okay. Hi everyone, a very good evening and welcome to week 7 of Data Science for Engineers problem solving session from NPTEL. I'm your TA Saladi Pravalika. I'm a Prime Minister Research Fellow and also a PhD scholar from Indian Institute of Science, Bangalore. Right? So just a second. Okay. So unfortunately, last week the chat has been disabled. So please use Q&A. Okay, and I will read all every message in Q&A and I will answer you and everything. Okay, please use Q&A only. Did I start recording? Yes, I did. Cool. So again, just a bit of instructions again. The session is being recorded and be respectful during the session. I will not remove to hesitate you from the session if you are being rude towards me or towards anyone else. And as I said, unfortunately, the chat is not working and hence use Q&A only, right? And if I am asking any questions, obviously I'm going to give as MCQ, right? So I will also raise a poll. You can answer the poll as well, right? So in today's topics will be dealing with some basics of neural network. I will not go deep into it, but I will definitely give you some things that you require to understand today's topics like parameters and hyperparameters, cross validation. And last week we have covered regression problem. So this week we are going to cover classification problem and then logistic regression. So logistic regression is a type of classification problem, even though the name itself says it's logistic regression, but still it's a classification problem. Okay, and we'll also look at some performance metrics. So how are we going to say if a model that we have done is good or not? Okay, so we'll look at two types of performance metrics. One is confusion metrics, and another one is ROC curve. Okay, so with that, let's get started. Right. So yeah, one second, and so I'll briefly cover little bit about neural networks. Okay. So last time you have remembered that I was talking about supervised learning and unsupervised learning. So still we are looking at supervised learning. So that is we have some training data which also has labels to it. For example, if X is my input to some model, okay, it will predict Y hat. This is prediction. But I'll also have some ground truth called Y. Okay. So this is a supervised learning. So I have both input and uh, an estimated output that I want. So this is the ground truth that I have. Okay. So I have this and that. Okay. So how does this work? Okay, we know that there is some input. We know that the model is going to predict something out, and we are going to compare it with something, and then we are saying, okay, if there is too much of difference between these two, then the model is not performing well. If it is, if y hat is closer to y, then the error is less, and all of that. So that whole part we have covered last week, right? So now we'll see what exactly happens in this model. Okay, just like how we have some neurons in our brain. Okay, imagine we are giving some inputs to neuron. Okay, this is a neuron. Okay, we'll take the example again of that real estate example. So in that we were looking at different kinds of inputs to get some output, right? So for example, how many number of bedrooms are there? What is the area of the building and all of that to finally predict what is the price of that building, right? So those all are our inputs. So we are giving multiple inputs to something, right? And some magic will happen here. And then I am going to get some output from the neuron. Okay. So I'll give some inputs to the neuron and then I'll get some output from the neuron. Right. So this is just one neuron, but that is not how things work. We'll have multiple such inputs, right? Multiple such neurons. Okay. And this I'm calling as my input layer. Okay. And if I'm considering the whole part here to be some model, I'll have some output layer. Let us say I'm doing a classification problem and to which I have three different classes. Then I'll have three neurons at the end. So that is my output layer. Okay. So everything that happens here is something that you're not seeing. Hence, we call it as a hidden layer, hidden layers. So here we'll have multiple such neurons. We are not sure how many. It can be any number of layers. So if I'm having three, it is a three-layered one. If I'm having, I can have one hidden layer. I can have two. I can have three. It's all up to me how I choose to build this model. So this is my entire model, right? So I give some inputs and all the inputs will go to each neuron, right? And similarly, then all, and I'll get some outputs, right? Okay. So, uh, yeah. And once my output layer gives me some values, I'll have some predicted values, right? These are my predicted values. And then I'll also have some true values, that is a ground truth values, ground truths. And based on the predicted value and the ground truth value, I'll get some error, right? So now what happens is these errors, this error which is there, I will take this error and I will do some back propagation. Okay. So that, see, I'm, it's basically in words saying to a model, see, you are predicting this, you are getting this much error, but you need to reduce your error. Okay. So this back propagation is basically like a feedback that we give to the model. Okay. So that it will change some parameters to get closer to the true value. So the main aim of the model is to get the predicted values as close as or equal to the ground truth values. Okay. So if the error is increasing, we'll do some back propagation where we are telling the model that you are having this much of error, reduce it. And then some parameters the model will change, and then it will give an output. It will try to give an output that is closer to the ground truth value. Okay. So how is all of this happening? Let's place it. Okay, just a second. Okay. So imagine this is my neuron. Okay. I'm having three inputs. Let us say X, Y, and Z. Okay. And my neuron should give me some output. Okay. So what exactly this neuron has is for every input, it will give some weight. Okay. I'm calling WX, WY, WZ as my weights. Okay. So here, these are some weights for me. Okay. And the neuron, every neuron also has its own bias. Okay. I'll add the bias as B. B is as bias. Okay. So now I have X, Y, Z as my inputs, WX, WY, WZ as my weights. So for every input, there will be an assigned weight. Okay. And for every neuron, there is a bias. Okay. And then we will get some output. Okay. We just Y hat. It can be something. Okay. Or we'll take a different, maybe K. Okay. So what I can write it as is this output here till here is X into WX plus Y into WY plus Z into WZ plus some bias. Okay, so the weight is multiplied with each and every input value. Okay, so then I will get some values, and then I'm going to add the bias of this. So these all are called as my parameters. These are called as my parameters. Okay, so then to this I will add something that is called as an activation function. We will look at these later. Okay, you might have heard of ReLU and all such things if you have started some kind of machine learning, deep learning, or you might have heard here and there. So even if you haven't heard of it, it's fine. We will cover it some at one point. Okay, we'll also have some activation function. Let us say if that we are representing as alpha, then I can put the alpha here. Okay, so this alpha times these parameters that we have. Okay, so yeah, so far clear. uh, please use the reactions if possible. Now it will be easier. I hope everyone is clear. Yes, cool. Thank you so much. um, Also, once again, I'm repeating, please use Q&A if you have any doubts. Okay, chat is still not working and I was not able to figure out why. Okay, still, we have only two classes remaining, so I didn't want to change the Teams link. So hence, I haven't changed. Okay, so I'm sorry for that. But yeah, uh, okay. So now we will look at parameters and hyperparameters. So this is parameters and hyperparameters are two essential concepts in deep learning, machine learning. So whatever you do, and these two names always pop up. Okay, so they are often confused, like confusing to us because okay, we'll see why because of the names and sometimes we call a hyperparameter as a parameter and vice versa. Okay, so let us break down the key differences before we go deep into all of this neural network stuff, right? So let's look at parameters. So parameters are something that is learned by the model. Okay, so parameters are the values that model learns during the training process. When we are training the model itself, we'll be learning. So they are essentially the weights and the biases that the model adjusts to fit the training data. So these weights and bias are called as the parameters, as I was saying earlier. So when this process will repeat for every neuron, right? So at the end, as I told previously here, we'll calculate the error or the loss, then we will back propagate, right? When this back propagation happens, I told the model will try to change some things such that it will come closer to the ground truth, right? So the values that the model is trying to change are nothing but these weights and biases. Okay, so these are called as the parameters, and hence these are trained while training the model itself. These are being adjusted to fit the training data. Okay, and these are part of the model. So they are integral components of the trained model. So if I am saving my model, like once the training is done, I have to save it. So when I say I'm going to save the model, it is essentially that I'm going to save the weights and the biases. Okay. So once the model is completely trained, these weights and biases and all of that are saved. And when I want to predict, like if I give an input of something to that model, it should predict something, right? So that prediction is based on these parameters. Okay. They are saved along with the model and used for making predictions on completely new data, like the data which is not being trained on. Okay. And their data okay, they are dependent on the data set. So parameters are directly influenced by the training data set. A model trained on one data set will have different parameter values than a model trained on another data set. So if I am saying I have trained a model based on cats and dogs images, And I can't take that same model and I can't really use it on, let us say, some ultrasound scans or MRI scans and all of that. Those are completely different from cats and dogs, right? So I cannot use the same model for both, and hence it is completely different, right? And the other one is called as the hyperparameters. So hyperparameters are something that you set before you start the training. For example, number of epochs, or how what the learning rate and all of that stuff. So, and the batch size. So batch size is basically like if I'm having 100 images, and if I say batch size 10, then I can divide 100 by 10. Then I'll get 10, right? So I'll have 10 batches. So that is not a parameter. That is something that I'm setting before I am even training. So those kind of things are called as hyperparameters. Okay, they are external to the model. They are not in the model. So they are not part of the training itself. Sorry. Even when we are saving the model, it won't be there inside the model. It won't be saved along with it. Okay, and they are completely data independent. So hyperparameters are chosen based on what problem you're solving or the knowledge that we have and experimentations. If I'm working on some deep learning problem, I give some standard values first, and then I might increase or decrease, or I might double the values and see. And if my accuracy and all are increasing, then obviously I am going to go closer and closer towards increasing or decreasing. Okay, that based on experimentation as well. Okay, they are not depending on the data. Okay, so as a whole, in a neural network, the weights and biases are some parameters that are learned during the training, while learning rate and also the number of hidden layers and number of neurons in every layer, batch size, and other epochs and all of that are called as hyperparameters. Okay, I hope so far everything is clear. Okay, so let's look at an example. So we have a model, a model design. Model design is nothing but an architecture. So I'll say how I want my model to be, like how many convolution blocks I have, how many layers, what kind of activation functions I want to use. And there are other concepts as optimizers and stuff. So what all I have in the model design. So I have that. Okay, so this is nothing but the architecture. And then I have my hyperparameters. So as you can see in the picture, they are like the knobs that you can increase or decrease based on your wish. Okay, so some are learning rate and dropout. Dropout is basically you are not going to use some neurons. So you define them. So dropout rate is this much and all of that. Okay, so using the hyperparameters and the model, whatever architecture that we are having, we are going to train the model, right? And then I'll be getting my model parameters. So model parameters are the variables learned from the data, such as weights, bias, etc. Okay, so this is all fine, but how exactly are we going to select these hyperparameters? Okay, parameters means because of the back propagation and everything, it will keep on trying to come closer to the true ground truth. So hence parameters are fine wherever they are started from. But how exactly are you going to use going to select what hyperparameter value that you want to give, right? So what we are doing is we have a data set. Okay, let us say I have like 100 images, right? I divide those 100 images into three parts. Okay, first part is for training, second part is for validation, the third part is for testing, right? So um, tra- training means we give x as an input, it will give y hat as an output, and then we have the ground truth y, error is calculated, and then back propagation is made, and then the model learns again, And this process overall continues, keep on continuing until our data set is over, the training data set is over, and also the number of epochs or something that we have defined before are over. Okay, so if I say 200 epochs, so this happens 200 times for different batches, and then finally the training will be done. Okay, if I'm saying I'm testing something, so once this training is over, I will get some model saved, right? So what I'll do is for testing data, I have something I'll give as an input to this trained model. Okay, this is trained, already trained. You are not training again. And this is going to give me some output, y dash. Okay, but I also have my ground truth. So we will see the difference between these two. And then we will say, okay, this much loss is there. Okay. Your model is predicting this, but this is the ground truth. So this is a some loss that I'm seeing. Okay, so that is training and testing. But then we also have this data set called as validation. So in the data set, we divide some part for validation purpose. So this validation data set that we are taking is going to tune or select whatever hyperparameters we can take. Okay, so how is that going to happen? We'll see. Okay, there are many methods, and out of which these two methods are something that I'm going to explain today. Okay, leave one out cross validation. Okay, so if I'm saying my validation data set is probably 100, okay, 100, or maybe just take 10. Okay, let us say I'm having 100 images total data set. I say I use 80% for training, 10% for testing, and 10% for validation. Then validation is equal to 10, right? So I'll take some 10 data points, and then this is my entire data point set. Okay, so in leave one out cross validation, what I'll do is I will leave one data point aside, use the rest of the data, that is, let us say if these are 9, I'll use these 9 to train the model and then test on this one. For different hyperparameter values, I will test on this. And then the process continues. Then I will leave this one out. I'll take the second uh, data point, and then I will again do the same thing over and over again. So this all and this one will act as the training data, and this one will act as the testing data for me. Okay. So in leave one out cross validation, I'm just taking one data point. In k-fold cross validation, we are going to leave out some values. Okay, if I'm saying k is equal to 3 or k equal to 2, that is easier. Uh, and if I have 10 data points, what I'll do is I'll divide them, these 10, into by 2, and then I'll get 5 groups in total. So I'll take 5 such groups, right? And one group I will use as, say, I'll call it as testing, and the other 4 as training. For one set of hyperparameters, I will get some, I'll train the model using these 4 batches, right? And then I will test this data on that. And then again, I will change some other hyperparameter. And then this time I will take the second last one for testing, and on the remaining data I will train. Okay, like that I keep on changing, and whichever a hyperparameter is going to give me the best value out of all, that I'm going to take, and then finally I will train my entire data set on that. Okay, so this is an example. So one I already told in the previously I told hidden layer, the number of hidden layers that we are going to take is also a hyperparameter. So in this graph it shows, so this pink color just took one hidden layer, whereas this orange line took two hidden layers. Okay, and both are having same number of neurons. Okay, so if I am taking three neuron numbers, right? If I see, I'm having error rate higher for a single hidden layer, but for two hidden layers, I'm having lesser error rate. And if I kept on increasing my neuron numbers at 10, my mean square error has decreased drastically for a two hidden layer, right? And then it has increased again. So from this graph, I can make an inference that at if I use 10 number of neuron numbers, and if I take two hidden layers with the same two hidden layers, then I'm going to get less error, right? And hence, to train my entire data set, I am going to use these values as two hidden layers with 10 neurons. Okay, so that is going to be my best hyperparameters that I can take. Is this clear? Is this one clear? I know this sounds too much, but yeah, sorry. But if it's not clear, please drop a message. This is as simple as possible I could go, uh, because it involves too much of background more than this, but still I have to cover all of this. Okay. Um, okay. I'll continue then. Okay. Here comes our most favorite questions, right? So far, I hope you all have followed. Okay, let's look at some questions now. What is the primary purpose of cross validation in machine learning? So cross validation is something that I have told just now, the previously, the K fold and the LOO, this one. Yes, LOOCV and the K fold. This is cross validation. So what is the primary purpose of cross validation in machine learning? Uh, Put a poll. You can say. I have put a poll up. You can respond, or you can also drop a message in Q&A. Okay. One person says B. Okay. So let's look at the answer. Yeah. So B is in fact the right answer. So the main purpose of cross validation is to evaluate a model's performance and assess its generalization to unseen data. So we are taking the validation data, right? So with that, we will try to analyze the model's performance for different hyperparameters, and then we will use that values hyperparameters on a different data, like the entire data set for training data. Okay. So, which of the following technique is not a commonly used cross validation technique? See. Okay, we'll see. Okay. So the right answer is train test split. So we have seen k-fold cross validation, leave one out cross validation, and stratified cross validation is also a type of cross validation. But yeah, so in train test split, it is nothing but we are dividing it into training data and testing data. There we are not having any kind of validation data, right? But for cross validation, we use validation data set, right? So hence, train test split is not a commonly used cross validation technique. Okay. Okay. Let's see two more questions. Which statement best describes leave one out cross validation? Leave one out cross validation is the first one which we have seen. Any answers? Okay. Hmm. Okay, the answer is B, is your right. And it divides the data into k subsets and uses k folds for training and one fold for testing. Okay, okay. So let's see the next one. Which of the following is an example of hyperparameter? So which of the following is an example of hyperparameter? A, the weight of a neural network's hidden layer. B, the learning rate of an optimization algorithm. C, the input features of a dataset. D, the training data used for model training. Hopefully, you will be clear between parameter and hyperparameter by now, right? So, yeah. So, let's look at the answer. It's the learning rate of an optimization algorithm. So learning rate is something that we set before we train the model. Okay. So it is a configuration setting and hence it's a hyperparameter. Okay. Okay. With that being said, let's start classification. Okay. Just a second. Yeah. Let's start classification. Classification is a supervised learning that assign class to the data points. Okay. So as we were if I'm giving you some images, okay, let us say this images belongs to cats or cats and dogs. Okay, you have I'll give you 10 images, all are a mixture of cats and dogs, and then you have to classify each of the image either as a cat or a dog, right? So that is a classification problem. That's the most general one. But technically speaking, we'll have much more deeper examples. So those examples are these: email spam detection. So if you open your Gmail, you will also have a folder with the name spam. So whatever the mail detector or the classification problem, classifier thinks that this model is a spam, then it will detect it. then I mean this mail is a spam, then it will send it to the spam folder, right? And then sentiment analysis. So there has been many projects for that. So if I am smiling, then the sentiment analysis model tells that okay, this person is happy. If I'm crying, it will say that the person is sad, and all of that. Image classification, the cats and dogs example, and medical diagnosis. So if looking at CT scans or MRI scans or ultrasound scans, sometimes the model also predicts if this person is having cancer or does not have cancer or things like that, right? And fraud detection, looking at some kind of maybe like messages or anything. They can say, okay, if you're getting a message from something, if you give this to a model, and then the model might say, this message seems to be a fraud or not a fraud. Okay, and language identification. So if I give something in Japanese, then the model will say, okay, this is Japanese. And if I have seen some language that I have absolutely no clue, I can give it to this model and it will identify the language for me. Also, there is, and most common example, if you open your Google Photos, it will classify according to each person, right? All the images in which your face is, everything will be as one folder. All the images that your brother or a sister is there, it will be in a different folder. And you can add the names and all, right? So it is classifying based on the images as well. So that is one example. Another one, if you're using Google Drive, it will classify you again. At the top, you can have this option where you can classify PDFs and PPTs and images and everything. So there are multiple such classifiers, right? Um, okay. So how are we going to construct such a classifier for ourselves, right? So there are some types of classifiers. Okay, these are the main two classifiers. Binary classification problem. So in binary classification problem, it just has two class. If I'll give you some image and you have to tell whether it belongs to class A or class B. Simple example. Sometimes it's a multi-class classification. So I'll have more than two number of classes, and then I have to say it belongs to which of those three or four classes it is. Okay, that is a multi-class classification problem. So here in the first image, if you can see, these all red symbols, the cross symbols, all of them are class A, or let us say class A, and all of these blue circles are class B, right? So this line here is a hyperplane that is dividing class A with class B. Okay, this is a hyperplane that is dividing both these classes together. And now here I'm having three different classes, a cross, a red cross, and green triangle, and blue rectangles or squares, whatever they are. Okay, and then these three hyperplanes, I have three hyperplanes here, and then it is dividing them into three different classes, right? And that is one type of a problem. And then we have another type of classification, and that is linearly separable and non-linearly separable. So here I have class A and class B, and this hyperplane is linearly separating class A with class B. In case if I can't separate something with this one particular line, like in a linear line, then we call it as a non-linear separable problem, right? So if I'm taking this whole data, I can't draw a line like this, right? I can only separate it this way. If I draw a circle here, then all the class data points will come into one, and the rest of them will go into a different one. And hence, this is a non-linear separable problem, and it's a non-linear boundary. Okay. And here comes the main thing that we are going to discuss today. It's logistic regression. I hope so far I am clear. If there is anything that you haven't understood, please let me know. Okay. Okay. So no questions so far. Yeah. So, logistic regression. So, in real world data, it is often noisy and uncertain. A simple guess of a class may not be that reliable. So, you have been trained so many times, so you look at things the way you want, and then sometimes there are some images where you can't differentiate what kind of a class that belongs to, right? So, a simple guess is not always a possibility, right? And hence, what we do is we take some kind of probability. Okay. This probability is provides a measure of how confident we are in that classification. Let us say I looked at something for the first time, an image for the first time, and then I might say, I'm not sure of this, but there is a possibility that this might be a cat. I'm not sure, but it might be a cat. Probably this is the thing, right? There is some kind of a probability in the confidence that I'm having in my classification of that image, right? So if I'm saying I'm highly probable that this image is of a cat, then it is then I'm saying it's strong likelihood that the data belongs to this one particular class, which I'm calling as a cat, right? So logistic regression is also a classification technique where we clear uh, draw linear boundary, right? So we use probability in this so as to understand better. Okay, we are going to classify better using this probability here. So the goal of logistic regression is, given a new sample data, we predict the class from which the data point likely to have been originated. So if you look at the image here, okay, we are considering uh, the green circle as 1 and red cross as 0. And I'm drawing a plane here, z equal to 6 minus xi. Okay, it's a hyperplane. And then I'm dividing it linearly. Okay, so I'll give a data point, and based on these values, based on my 1 or 0 values, I'm going to put it in the hyperplane. If it is greater than this 0, it will be at one point. It will be less than this, it will be at another point. Okay, so we are going to predict which class it is from. The two classes that we have here is green circle and red cross, right? So we are going to simply guess the class. The simple guess of a class is not good, and hence we use some probability to provide a better understanding for us. Okay, how are we going to use a probability in this? So if we are classifying two classes, right? Two classes, we use a decision boundary. Okay, so if you can if you look at this function here, f of x is equal to 1 by 1 plus e power minus x, you will have any values starting from minus infinity to plus infinity. So we are saying we have to use probability. Probability ranges from 0 and 1, that also we know. And this is called as a sigmoid function here, this f of x. They are commonly used in machine learning to model probabilities. Okay, because they map any kind of real input values. Real input values here is nothing but the x in f of x. Okay, to a value which is in between 0 and 1, which can be interpreted as a probability, because probability is always in between 0 and 1, and hence we are taking this sigmoid function as as a probability. Okay, as you can see from the graph, the sigmoid function approaches 0. um, okay, the sigmoid function approaches as 0 where if this x is going towards minus infinity, the sigmoid, this function, is going close to 0, right? And approaches 1 as it is going to 1. So this is 1, this is 0, and it is going to 1, approaching 1, as well as the x goes towards plus infinity, right? and it is always in between the 0 and 1 values, and hence we take this as our probability. Okay. So we already also have a linearly bound. If we have a linearly bound equation, this equation we have seen previously in the previous class. There we were writing it as y is equal to beta 1x plus beta naught, where beta naught is the intercept and beta 1 is the slope, right? We're taking it like this, and then the slope is beta 1, and this is beta naught, right? I hope you all remember it. Any questions so far? Okay, yeah, good. Okay, yeah. So we have y is equal to beta 1 x plus beta naught. Here we have just written it as z. And then to this, we apply a sigmoid function, right? So this sigmoid here is nothing but an activation function that I have discussed way before here. Yeah. So as I told here, we use an activation function. So in this lecture, we are we are using uh, sigmoid function. Okay. In this lecture, we'll be using a sigmoid function, and hence we will go there. Okay. Yeah. So we are going to apply sigmoid to this, right? Sigmoid f of x is equal to 1 by 1 plus e power minus x. So here, this x is nothing but the input. The input is this, right? So if I have to write this in neurons form, if I'm giving x as an input and it has a weight of wx, and this is my neuron with bias b, then I can write this as x into wx plus b. I hope you remember this from the previous one, right? So to this is nothing but this. Okay. To this, I am applying a sigmoid function, and hence I write f of x is equal to 1 plus 1 by 1 plus e power minus of x into wx plus b. Okay. X is the input value. Wx is the weight that is assigned to it, plus b is the bias. So bias is basically like you are not going to anytime that you get a data, anytime you're giving an input, it is not going to be a clear data. You will always have noise in the world, right? So bias is something that you are adding to a neuron so that the model will know that anytime that you give some input, there will be some bias to it. Okay. So it is basically making sure that the model is not going to overfit for the training data that you are giving as for training. Okay, you are not going to overfit it to the data. Rather, it will be having some noise. You are adding some noise so that it can learn so that it will be easier for other data also to be predictable. Okay. Um, so yeah. So after the activation function is added on this xwx plus beta, this is the function that we are going to get. This is the final output that we are going to get. Okay. So as we can recall, I have the neuron with a bias B and with wx, and then I'm applying an activation function, and then I'm getting some output as y, right? Now I have to calculate the error between what value I have got and what value I am supposed to get. Okay. Here, if we are taking a binary problem, here y is equal to 1, y equal to 0. Let us say that is the predict true values. Okay. So we are getting some y dash, right? Now, this is a loss function that I'm going to use to calculate the error. Okay. So now to we use this loss function. Loss function is to calculate the error. Okay. So this loss function will tell me, okay, if you are giving x as an input, you got y hat, and this is your, this is y. It's nothing but y hat. Okay. So if this is your y hat, this is your y, and this much loss function is there for you. Okay. So that loss function, whatever error we are calculating, we will give it back. Here it's not there. We will give it back again, and the weights and the bias will be updated such a way that this error or this loss is reduced. Okay. So this is a graph for one single epoch, right? So here you can clearly see that I have two types of data. One is red, one is green, and then I have this decision boundary here, okay, which is a hyperplane. So I'm saying all the values above this are of one class, all the values below this are of a different class. The first time when I train, I have got it this way. All the datas are on one side of the decision plane and it is not being classified at all. So this is only for one epoch. I might consider doing it for different epochs. Okay, so the weights will get updated. So and then I might get all the red ones here, all the red ones on this side, and all the blue ones at this side. There will be some here and there, some misses or mismatches will also be there. So loss is definitely going to be there because we are using bias so that the model is not going to fit for only for this data, right? So hence here and there you might have some misclassifications also. Okay. So you have to keep increase, you have to use more number of epochs, not too much and not too less. Okay, if you are taking too much, then it will take a lot of time for your model to train. So I prefer taking like for the first time I'll take like 50 epochs and then I usually go to 150, 200 and then 300 and later I'll decide if I want further on. Okay. So let's look at some questions. Okay. Um, what type of machine learning problem is logistic regression primarily used for? What type of machine learning problem is logistic regression primarily used for? A. Regression. B. Classification. C. Clustering. D. Dimensionality reduction. B. Okay. Anyone else? Any more answers? So, yes. Classification is the right answer. Logistic regression is a classification algorithm. Unlike its name, in the name you see regression, but no, it's a classification problem. And we use probability for the outcome. Okay. And then, yes, next question. In logistic regression, what is the output range of the logistic function, the sigmoid function? What is the range? And I can draw it here. This is x, this is the sigmoid function. Sorry. So this goes to minus infinity plus infinity. What is the range? Yes. Okay. Okay. So the range here is 0 to 1. Range is something that we say as what kind of outputs that we are going to get. So here, for any values of x, the maximum that I can get is only 1. And here, for any kind of x values, I am going to get only 0. So my range is going to be 0 to 1 only. Range is the output that I'm going to get. Okay, right? So 0 to 1 is the right answer. The logistic function outputs probability. So it's basically the probability as we were discussing earlier. So it's in between 0 and 1. Okay. So hence we use sigmoid function for mostly for binary classifications only. Okay. And some more questions. What is the purpose of the sigmoid function in logistic regression? What is the purpose of the sigmoid function in logistic regression? A. To convert odds to probability. B. To model the linear relationship between features and target. C. To normalize the feature values. D. To normalize the mean squared error. Okay. Okay. A. Okay. Right. So let's look at the answer. So the answer is A. To convert odds to probability. So basically, the sigmoid function, it's going to map the log odds to a probability value in between 0 and 1. So this log it is nothing but the x values that we were taking, right? So we are going to put it in the sigmoid function and then it is going to give us zeros and ones. In logistic regression, what is the cost function that is minimized during training? I don't think I have covered this. So I'll just go back and I'll just show it to you. So this is the loss function that we have used. Okay. In logistic regression, we are using this loss. Okay. And we call, sorry. Okay. We call that loss as cross entropy loss or the log loss. If you remember, let's go back and show it again. Okay. We are using logarithmic values to calculate their loss, and hence we also call it as a log loss. And it's also called as cross entropy loss. Okay. It is used as a cost function in logistic regression. Okay. Uh, okay. Um, in logistic regression, how are the model coefficients, that is weights, typically determined during training? Uh, so this is not something that we have covered. So hence, we'll just say, okay. So the answer is we calculated using gradient descent. So gradient descent is not, as I was saying earlier, we use a back propagation, right? So I said we have a model and it is predicting y hat, and if I this y is my ground truth, then whatever loss that I got, this is going to go as a back propagation, I said, right? So gradient descent is one such thing where I'm going to update my weights, okay, W plus some change I might make, okay. So initially, if my weight is W, I might add 0.001 or add 0.01 based on whatever values that I'm taking, okay. And I try to calculate, I try again with a different delta W nu is equal to W plus delta W. So with whatever values now, my new W value, I'm going to calculate the y hat again, and then I'll get some loss, and again I'll go back. I will again make some, I'll add or subtract some delta W, and then I will calculate the y cap again. Okay, so as to minimize the loss. So whichever has the least loss, I will take that one. Okay. Um, cool. And then, yeah, which evaluation metric is commonly used to assess the performance of a logistic regression model? Okay. mm, So these are some evaluation metrics that we use. I haven't, we'll discuss it later. Okay. So we look at the accuracy of the model, like how accurate our outputs are, and then precision, recall, and F1 score. We will see when we are dealing with the performance metrics and all of that. Okay. Okay. So now I would like to shift to R Studio. Here I have a data set. This data set has been uploaded on Drive as well. Okay. Either if you want to do it now itself, you can directly take that data set and you can look at it. It's a CSV file. Okay. In that so in that CSV file, I have seven different types of inputs. Okay. Perimeter, area, compactness, length of the kernel, width of the kernel, etc. etc. Kernel is this one thing. This one thing is called as a kernel. So different kernels we have here. So it's basically like I have a model and I'm giving seven inputs. Okay, seven. One, two, three, four, five, six, seven. And then I'm going to get three types of outputs like seed A, seed B, seed C. Let us just say I have three classes of seeds, seed A, B, C. And then the model will basically tell I am 0.7% that it is model A, 0.1% it is model B, and 0.2% it is model C. Right? I'll pick the highest probable one and I'll take A as that type. If at all 0.7 is this, then I'll say C is my output output class. Okay. So with that being said, let me go back to this. Stop sharing. Okay, it's 7. So why don't you guys take a 5 minute break? Let's be back by 7:08, or I might. Okay, let's be back by 7:10, and then we will start our studio. Okay, and then we will be back. Okay, by 7:10 we'll be back. Okay, so let's start again. Okay, so I'm sharing my screen. So this is the R code, and I am using a data set here. So this data set, wheat data set. Okay, so it's basically seed data set. I have shared it on Drive, and I have just posted the Drive link as well. Okay, if you're interested, you can download it and you can simultaneously see how the file is, okay, what kind of data is there and everything. But if not, I will also share everything there. Okay, so here I am reading the CSV file, okay, using read.csv. Okay, and then, sorry. So now I have read the CSV file and I have stored it in the variable name data. Okay, then I'm printing how the head looks. Head of data means the first six values it is going to give me. Okay, so it has something as an ID, so it will have many numbers, and then it has area. Okay, so and then perimeter, compactness, length of the kernel, width of the kernel, and different coefficients. Okay, so total seven features, and finally what I have is the seed type. So I have seven inputs starting from area till the length of the kernel, and my output label is a seed type. Okay, so here you might have a doubt. So all the seed types here are just 111. So I'll print the tail also. Tail means from the bottom, the last five or six values, six values. Okay, here you can see the seed types are three, right? You can open the CSV file and you can see you will have seed types of starting from one to three. Okay, so I have total of 210 data points, right? So in this 210, I might have values here and there where there is no data. So so in such cases, I don't want that data to be there. I will just remove the entire thing. Okay, is .na of data will remove any row that has or not I mean not a number or any kind of a thing it has, it will be removed. Okay, I'm summing it up and I'm seeing in this particular data, fortunately there is no more NA, right? Then I'll see the dimensionality of the data. So I have 210 datas, and then I have nine columns each. So I have nine columns here because I have seven features, one output label, and one with the name ID. Okay, ID is nothing but the numbers one, two, three, four, and all of that. So overall, now I have nine columns and 210 rows. So 210 data points I have. Okay, so far clear? So far clear? Okay. Um, and then I want to see the structure of the data. Uh, the structure of the data is going to show me what are there in every column. So for ID, you all know it's one, two, three, four, and all of that, and it's an integer data type. And then I have area, and it's a numeric value. It is in points and all of that. So the area here is the area of the kernel. Okay, and perimeter of the kernel, compactness, length of the kernel, width of the kernel, and so and so forth. All of these other things are there. And I got to know what data types they are and some of the values, like the starting, beginning values. Right? And then now I want to take the summary of the data. Right? So a summary of the data usually gives me the minimum value of all, and then the first quartile range, mean, median, third quartile range, and the maximum value of all. So if I'm looking at area, I can say that there is one kernel which has a minimum value of 10.59, and a maximum value of 2.18, and the rest of the kernel areas are in between these two values. So same thing for perimeter and compactness and all of that thing, right? So so I'm using a different library here. This library is called Caret. So in case if you have missed previous sessions, so you basically go to tools and install the package called Caret. Okay, Caret. And then after the installation is done, you can directly call the library. You only have to write library open bracket and Caret. Okay. So you can run it, and then I'm setting a seed, and then now I want to partition the data. So the overall data that I have is 210. Now I'm going to divide the data into training and testing. Okay, here I'm not taking validation. So I'm just simply taking training and testing data. Okay, I'm creating a partition. Oh, sorry, so here what I'm doing is I want 80% of my data for training and the rest of the data for testing. Since I have given 0.8. If I want training and testing to be 50-50, I can give 0.5, p equal to 0.5. In case if I want my training to be training data to be 60%, I have to give p is equal to 0.6, and so on and so forth. Okay. And then I have to write here. So I have to say rest of the data. So this is my output. So in the data variable for the column C type, this is going to be my label. This is going to be my ground truth. My ground truth is seed type, right? Any questions so far? Okay, no questions here. Good. Um, so I'm putting the index as 80% training and 20% testing. And then I'm saying the seed type column in the data or data set called data, that seed type is going to be my label, right? And then I'm dividing it into 80-20 percentages. Okay. So I'm taking training is equal to data of index. So index here is this 80%. So training, it will take some values, and the remaining values it will take for testing. Okay. Now let us see the training and testing data length. So now my training is 168 and my testing values are 42. If you sum both of them up, it is 210, which is my overall data set, right? Okay. So now I want to do, since I'm having three classes here, C type is 1, 2, and 3. I have three types of classes, right? Hence, it is a multi-class classification problem, right? For this, I am using a library called as tidyverse. Okay. Again, if you haven't used tidyverse before, go to tools, install it, and then call the library here. Okay, I'm just giving library tidyverse, right? And now I am going to use something called as NNet. NNet means neural network. Okay. And then I'm giving something called as multi-norm, which means multi-class classification. And then I am defining this is my label tilde. And then if I'm giving a dot, it means except this seed type column, you have to take every other data as an input, and the seed type is my output. Okay. And I am defining what is the data that it should take for training. So data equal to train. Okay. And it is learning something. Okay. It has given some weights, and then it has taken some initial value and some iterations it has done, and finally it has converged into something. Okay. Now some training has happened on the model. Okay, some neural network it has used and it has done something. Now I want to see the summary of it. I the so okay. So we have the coefficients for each coefficients and the intercepts for each and every parameter, for each and every input that we are taking. It's clear. Okay. Uh, yeah. Okay, so mm, okay, this is a summary of the model. Now I want to do some prediction. So my model is now trained. Okay, now I want to do the prediction uh, on this model. So my prediction is going to be on my test data set, right? And hence I use the word predict, and then I use the model that it has been saved on. This is where the trained model is saved. Hence I'll give the trained model name, and then I'll define new data is equal to test. I'm going to test it on the data set, right? And then I'll say it's a classification problem, so it's a class. And then I will run it. Okay. Now I want to see what kind of predictions did it make. Okay. So how much was my training data? My training data was 42. 42 training data I had. So it was telling me the initial ones had 111 and then 222 and all of those. So for 42 data I had different classes. It has classified in this way. Okay. And then um, yeah. And then okay. So now I want to see if it has made classifications. Now I want to see something called as a classification table. Okay. So so this is true value versus predicted value. If my true value is 1 and my predicted value is also 1, how many are there? Okay. This one in clear we will be seeing in later parts of the problem. Okay. I mean, in the later part of the class, I will explain it much clearer there. Okay, so this is a classification table, also called as confusion matrix. Okay, and then we can calculate the accuracy. So you're going to take the sum of the diagonals of this. Okay, sum of the diagonals and the complete sum and into 100, and then you'll get an accuracy. Fortunately enough, here I have got 100 accuracy, but usually that is not the case. Sometimes it will change as well. Okay, or in place of this you can also call it something as a confusion matrix directly, and then you will get sensitivity, specificity, and all of these things. We will see it in the later part. Okay, this is the statistics for all the classes and overall statistics these are. So accuracy 1 here indicates that it is 100% accurate, and CI here is a class interval, and p values and all you don't need it right now. Okay. um Yeah, but with this, I'll stop the R code. Let's go back to the theory part. What do you want me to repeat? Please let me know what you want to repeat so that I can repeat it again. Okay, if not, I will explain the R code again. Okay, now done. Cool. Fine. I'll just share my screen again. Just give me a second. Here is the screen. Okay. Okay, so let's go back to some problems. One hot encoding. So one hot encoding, I'll explain this first, then you can try to solve it. In Let us say I have some classes. Okay, give some three classes as an example. Any three classes of almost the same type, like cat, dog, and something. Three classes of your choice. We can take that. Any three classes. Okay. So we'll take three classes. Maybe let's say bread, butter, and then jam. Let us say bread costs maybe 50 rupees. Okay. The butter, one slice, let's say it's cost 5 rupees, and jam maybe the 20 rupees packet. Okay. So this is usually the prices, right? So now what I can do is I can write it as a table: bread, butter, jam, and output is price. Okay. So if I take one bread and all of these are zero, then I can write this as 50. If I take one butter, then I can write it as 5, and one jam 20. So basically, I am representing something which is in words. So these are three categories, right? So I'm taking something which is in words, and then I'm writing it in the form of binary values, zeros and ones, and then I am get this is a different one. So this is an output. So these are my inputs, right? So these are my classes, different classes. I'm writing them in terms of zeros and ones, okay? And this is exactly called as one hot encoding, okay? So basically, we use this for classifications, okay? So based on this theory that I just said, yes, the answer is B, encoding categorical variables as binary vectors. Okay, so it is a technique to represent categorical variables as binary vectors to make them compatible with machine learning algorithms. Okay, so you might learn strings, you know words, so you will understand if I say, if I take a bread packet and I'll show it to you and I'll say this is bread, then you will understand. But how will a machine understand? It will not understand just by the word bread, right? So you have to give everything in terms of binary format to it. So for that reason, we use one hot encoding. Okay. In binary classification, what does precision means? So uh, let us say we have different terminologies here. Okay. Let us say we have a binary problem. Okay. It should say yes or it should say no for some kind of an input. Okay. If my model is this is my predicted value, this is my actual. If my predicted value is yes and my actual is also yes, then it is called as a true positive. So it is a yes, and then my prediction is also saying yes, then it's a true positive. If my prediction is saying yes, but my actual output, my actual true value is a no, then my model gave me a false positive. It is not positive, but my model is saying yes, it is a positive value, it is yes. So then it is a false positive. Okay. So precision is nothing but true positive by true positive plus false positive. This is called as precision. So based on this, what do you think is the answer for this question? In binary classification, what does precision mean? Measures. Okay. So yes, you're absolutely right. The ratio of true positives to all positive predictions. So all the positive predictions it is making is nothing but true positives plus false positives, right? So the precision is equal to true positive by true positive plus false positive. Okay. So precision measures how many of the true positive predictions made by a model are actually correct, indicating the model's ability to identify. Oh, sorry. Uh, yeah, sorry. Option A is also an answer. The ability to correctly identify the positive instances. So, what, how good is it in predicting positive values? So, let us take for an example. If true positives is equal to maybe out of 100, it is giving 80, and False positives, maybe it gave 5, then 8 by 85. We'll see how much it is. I just took random numbers. 80 divided by 85 is 0.9411, which means the model can predict positive instances by 94.11 percentage, right? So this precise the model is, we can say. Okay, so hence we have two options. It will identify how correctly it can identify the positive instances, as well as also the formula itself, the ratio between true positives to the total number of positive predictions. If it is making more false, I mean, false predictions or also false positives also, then this value will increase more and the precision will decrease. Okay. So, yeah, coming to the final topic, it's performance metrics. Okay. In performance metrics, at the top, we have the prediction class, and at the side, we have an actual class. So, let us say a patient has come to you, and then he has maybe diabetes, or he may not have diabetes. Okay. Mm, two cases: diabetes, he is a diabetic, not a diabetic. Two cases we'll take. Okay. So, if the patient is actually having diabetes, and if I say, yes, you are, if I'm saying the patient, yes, you have diabetes, then it is a true positive. Okay. If the patient has diabetes, and if I say, no, you don't have diabetes, it is just in your head, then it is completely a false negative, false, false sorry, he has now I'm confused. He has, and I'm saying no, then it is a false negative. Okay. So I'm saying the patient, no, you don't have diabetes, but in truth, he has diabetes. Then it is a false negative. Okay. And then we'll take an example when the patient is not having diabetes, but I say, no, no, you have diabetes. Then it is false positive. Okay, now in case if the patient is having not having diabetes, and if I say you are not having diabetes, then it is true negative. Okay, so far clear? True positive, false negative, false positive, true negative. If it is not clear, please let me know now itself so that I'll explain it again in much better way possible. Hmm. You have understood. Hmm. Okay, so these are some of the terms. Okay, you need me to repeat. We'll do one thing here. Okay. So there is an example of actual and a COVID test. Okay. Let us say a person has positive. The person is actually COVID positive, and the COVID test told he is having COVID. Then it is true positive. He is having COVID, and the test also said the person is having COVID. So it is a true positive. In reality, the person has positive, but the COVID test is saying, no, you don't have a positive. It is giving a negative value. Then it is a false negative. Okay. So here, this is true. Here, this negative is false. Okay. So you can say this is a wrong answer. So this is an F. So you write that F, and it is giving a negative value. So write the N here. Okay. Sorry. So now the person doesn't have positive COVID. And then the COVID test is saying, no, this person has it. The COVID test is saying the person is having COVID. Then that is a false answer, right? So we'll say this is a false positive. Okay. And then in actual, the person is not having COVID. And then the COVID test also says the person is not having negative, which is a true value. which is true, right? Then it is true negative. Is it clear now? You can compare the actual with this, and then you can write which is true, if it is true or false. Based on that, you can write which type it is. Okay. Yeah. So similarly here we have positive, negative, positive, negative. So that table has been put into a box for now. Okay. So if the patient is having a positive COVID, and then the test is also saying yes, it is positive, then it is true positive. And then if the patient is having positive COVID, but the test is saying no, it is wrong, then it is a false negative. And FP and TN also is something that you know, right? And here are some important things: sensitivity, specificity, accuracy, negative predictive value, and precision. So these are some of the important aspects that you look at for a model. Okay. How precise is my model? This precision we have seen, it is true positive by total number of positive values that the model is making. So this true positive divided by sum of these two is my precision. Okay. Similar to precision, we also have negative predictive value. So how much it is predicting negative. So this is just opposite to precision, which means it is taking true negative, how many true negatives it is giving out of all the negative values it gave. Okay, here we are looking for how many positives, here we are looking for how many negatives. So that is a negative predictive value. Okay, and then we have something called as sensitivity. Sensitivity means true positive divided by true positive plus false negative, this part. So it's basically like the person is having a positive COVID. Okay, so you are detecting this much of right among this much of wrong. So it is okay. It is uh, taking ethics into consideration. Okay, let us say your neighbor has got a COVID. Okay, he got COVID, but then my test told me that your neighbor is not having COVID. So the person will come back and he will come and meet you and he will be like, see, I don't have COVID. My test came back negative. And next day you will fall sick, which is basically not something that you want, right? So, so that false negative should never be there. The false negative should be as less as possible, right? And hence, it is the sensitivity is that you someone is having a positive value, that true, and you are detecting it this much, true positive value you are detecting this much, TP divided by TP plus false negative. If your false negative is increasing, if your false negative rate is high, then the sensitivity level goes down, right? And if the model is not sensitive enough, then we are not going to use it. Okay, especially for biomedical problems. Okay, and then we go for specificity. Okay, specificity is true negative divided by true negative plus false positive. So now let us say the same neighbor, he is not having COVID, but then he got tested. Now, even though he's not having COVID, if the test says that he is positive for COVID, how what does he feel? He feels like so burdened, pressured, and he all kinds of emotions he will go through, right? So for that, so for that we look at the specificity. So it's fine even if we get some false positives here and there, okay, once in a while, but not too much. We don't want false values at all. We always want true values, true positives or true negatives. Okay, so this specificity is the measurement of true negatives divided by true negatives plus false positives. So how much specific is my model? Okay. And then the main thing that we usually look at is accuracy. Accuracy is sum of true values, true positive plus true negatives divided by sum of everything. All the true values, all the false values, everything. Okay. So this is accuracy. So these are some of the formulas that are really important to look at your performance metrics. Okay, let's see some questions. So once the questions are done, we will probably wrap up. Okay, so what is the purpose of a confusion matrix in classification? Confusion matrix is the performance table that we have seen in the before one. Okay, so what is the purpose of confusion matrix according to you in classification? B. Yes. It is to assess the performance of a classification model. So, a confusion matrix is used to evaluate the performance of a classification model by providing information about true positives, true negatives, false positives, and false negatives, along with specificity and sensitivity, accuracy, and all of that as well. Okay? Okay, next. In binary classification, what does precision measure? Sorry, the same question is repeated again. So A and C that you already know. It's the ability to identify the positive instances, and also it is the ratio between true positives by total number of positives it is predicting. Okay, let's do some calculations now. So in a binary classification problem, if a model makes 80 true positives, so true positives is equal to 80, and then 10 false positives. False positives is equal to 10 and 5 false negatives. 5 and then true negatives are 105. What is the accuracy? Can anyone calculate? So you have all the four values. So you know the accuracy formula. For a quick recap, accuracy means the total true positives plus true negatives divided by everything. All the true values divided by all. Correct predictions by all the predictions. Can calculate. I have written the formula also. You can calculate it. 0.92. So, okay, let's look at it. Yes, you're absolutely right. Uh, Accuracy is 0.92 for this particular model. Okay, so let's look at the next one. A classification model predicts 120 instances as positives. So true positives plus false positives is equal to 120. So total number of positives it is giving is 120, right? So it can be true or it can be false as well. And then out of which 100 are actually positives. So true positives is equal to 100, right? From this, it means false positive is equal to 20. What is the precision of the model? What is the precision of the model? Precision is equal to true positives by true positive plus false positive. 0.83. Yes, you're right. So the answer is 0.83. Okay. So the last and final topic is ROC, receiver operating curve, operating characteristic curve. Sorry. So it's a uh, graph between sensitivity and 1 minus specificity. Okay. So yeah. So what we do is we take this graph. I mean, we take the values of all the sensitivities and the specificities, and then we try to draw a curve. Okay. So in a random classifier, you will only get a line, but if if at all a classifier is perfectly right, like it's 100% right, then it will have a sensitivity of 1 and false positive rate, that is 1 minus specificity as 0. So if it is close to this, then it is 100% perfect, right? So now if I plot a graph, if I get this blue one, this blue is the best graph ever. Okay. And if it keeps on decreasing, then it is the worst classifier ever. Okay. Mhm. Okay, so basically we are using this to visualize the performance of the binary classification model, just like the other table that we were looking at before. Okay, so they plot the true positive rate, the TPR, on the y-axis against the false positive rate on the right x-axis. That is 1 minus specificity. Okay, so TPR is nothing but the sensitivity, and FPR is nothing but 1 minus specificity. Okay, and then okay, so you if you want to see what this is, so a random classifier is a diagonal line starting from 0 0 to 1 comma 1. Okay, so that is a diagonal line which is a randomly guessed one. And if at all any curve that is on the upper left corner, then that indicates it is a better classifier. Okay, it means it has higher sensitivity, that is true positive rate. It identifies most positive cases while maintaining minimum false positive outputs, right? So now if you are saying the area under the curve, so if I'm for the blue one, if I'm taking the all of this will be the area, right? So this blue one is better, I'm saying, and for my green one, all of this will be the area. So as my value increases here, my blue one will have a higher area compared to the green one or the orange one, right? So more the higher the area is, I'm saying the better my model is going to work. Okay, right. So we'll quickly complete this, and with this we'll be done completely. Okay. 1 minus specificity is nothing but the false positive rate, like how much false positives we are giving out of all the positives that we have. You can put 1 minus and the specificity formula here. You will get the false positive rates. False positive by total number of positives. Okay. Yeah. So if a classifier has a true positive rate of 0.90 and a false positive rate of 0.15, what is the specificity? Okay, I'll write it here. So specificity is equal to 1 minus false positive rate. Okay, right? This is something that we have seen here. So I can say 1 minus 0.15, which is 0.85. Okay, is this one clear? Okay, next, a classification problem has 120 true negatives, 120, and false positives is equal to 30. What is the FPR? What is the false positive rate? So false positive rate is nothing but false positive divided by false positive plus true negative. Okay, how many false positives given? Okay, so which is nothing but 30 by 30 plus 120. Okay, it should give 0, 150, 1 by 5, so 0.2. Huh. 0.20 is the answer. Okay, 0.8. No, false positive by false positive plus true negative. Okay. Okay. So with this, we are done with today's class. Okay. Have a great weekend, and let's meet again the next week. And next week is our last class, but after that also, there will be an additional session for 2 hours, and you will get a mail shortly related to that. If you are interested, you are always welcome to join. Okay, so thank you all. Thank you for all the responses today, and you guys have been wonderful. And thank you so much for joining. And have a great weekend and good night. Okay. Bye everyone. Stop the recording. Thank you. Okay.